section 5.7 is applying the fundamental theorem of algebra, and quite honestly is just a review of section 5.5 and 5.6 put together. So these problems are going to be possibly lengthier problems, but none of the process involved is anything that should be unfamiliar to you. So what is the fundamental theorem of algebra? And really, you don't need to write this down because it's much, much, much easier than it might look. So the corollary says if f of x is a polynomial of degree n, then the equation f of x equals 0 has exactly n solutions. I'm going to stop there and just give you an example. If f of x is some polynomial function, so I'll just make this up, of degree n, okay, so the degree is 3, then when you take f of x and set it equal to 0, so if I replace this with 0, I know that it's going to have exactly n solutions, so it's going to have 3 solutions. Like I said, this is nothing challenging or nothing that you shouldn't know, right? So the degree just tells you how many solutions you'll have. However, we're going to add on to that, provided each repeated solution is counted as 2 solutions. Each solution repeated 3 times is counted as 3 solutions, and so on. So we'll talk about how in the world do you know if you have a repeated solution next, but if you have a third degree function, possibly one of those solutions is repeated twice, and that means that you have 2 solutions, but it's just repeated, and then you might have the third solution being something else. And again, I'll give you examples of that. Okay, so here's your example of a repeated solution. So for the equation f of x equals 0, so again, if your polynomial equation is set equal to 0, k is a repeated solution if and only if the factor x minus k has a degree greater than 1 when f is factored completely. Okay, now let me give you an example to make sure that this makes sense. So let's say you have some function and I ask you to factor it. Okay, so you go through all that work and it factors down to this. Okay, what does that tell you? Okay, so a repeated solution is when you have a factor that has a degree greater than 1. So here's my factor, but it's squared, so the degree is greater than 1. So that means my solutions are going to be, and you should know this, at -1 and +3. Okay, now I have a third degree function here, right? Because this is squared and this is times another x. So x squared times x should be x cubed, which means I have 3 solutions. So this counts as 2 solutions. Okay, and that's what a repeated solution is. So this counts as 2 solutions. So just a little sidebar there. So I really actually do have 1, 2, 3 solutions. Now, what does that look like on a graph? Okay, something else you should note. If I just sketch a graph here, let's say it's -1, and let's say here's +3, and this is a cubic function, so it might do something like this. Okay, if it touches but doesn't cross through, that counts as a repeated solution. So that point at -1 I know counts as more than 1 solution. Now if all I gave you was the graph, you don't know if it repeats itself twice or 3 times or 4 times or 5 times, and I promise you that at this point in your math career you don't have to figure that out, but you have to recognize that when it touches the x-axis that would count as a repeated solution. Okay, so make yourself a big note visually. If it touches the x-axis but doesn't cross through, that counts as a repeated solution. If it crosses through, it only counts once. Okay, so quick couple examples here. It says find the number of solutions or zeros, and pause the video. See if you can do this, because this should be like the easiest problem you ever do. Okay, so the first one is x cubed minus 3x squared plus 9x minus 27. What is the degree? You should recognize for sure that the degree is 3, which means it has 3 solutions. Now, do you know that all 3 of them are real? Or some, maybe there are 2 imaginary and 1 real, maybe there's some irrational versus rational, maybe there's a repeated solution. No, none of that you would know just by looking at that equation. yet. Okay, the second one is x to the fourth, so that's a fourth degree, which means you have 4 zeros. Okay, so this should be no problem. Okay, this problem says to find all the zeros for f of x, and note it's a very large polynomial function, but it is a fifth degree function. Okay, so that's the first thing that you should note. So I have a fifth degree function, which means I'm going to have 5 zeros. Now, you're going to find all 5. So like I said, some of these problems just get quite a bit bigger. So this would be a calculator question, okay? However, I still want to see all of your work, and I'm not going to fit that word there. So you need to note that just because you can use your calculator doesn't mean you can say, well, I found that zero on my calculator. You're definitely going to use your calculator to help you save time, but you still have to show me all possible algebra. So take a second, pause the video, and put this into your y equals on your calculator and take a peek at the graph. When you graph this, and I'm just going to kind of zoom in on what the graph, when you graph it, what it actually looks like. So when you graph it, it looks like this. Okay, so it is touching at -1 and it's crossing through +2. Now, according to the repeated solution theorem, you should recall that this counts as two solutions, or I'm sorry, it counts as a repeated solution, and this counts as one solution for sure. So at the very least, you have 1, 2, 3, if it only repeats twice, 3 solutions. What does that tell you about the other 2 solutions? They have to be imaginary because this fifth degree function is not crossing or touching the x-axis anywhere else. So I have no choice but to work this fifth degree function synthetically down to a quadratic function so that I can solve that using the quadratic formula, because there's no other way to find imaginary solutions. Your calculator won't find those for you. So I might list some possible rational zeros, and this is nothing new to you. So all the factors of 14 divided by all the factors of 1. So that's going to be plus or minus 1, 2, 7, and 14. Okay, then I could sit and try some of those. However, here's where your calculator is going to benefit you. I can see that -1 is a solution, and that's a possibility, and +2 is a solution, and that's a possibility. I can also see that -1, I can reuse that twice, okay? And I'll tell you, for purposes of Algebra 2, your repeated solutions are only going to repeat twice. So don't worry about distinguishing how many times it repeats. Just think twice for now. So here we go with the process. I'm going to do synthetic. I'm going to take all those coefficients, and I believe we have every degree. Yes, we do. And I'm going to start with -1. Now, please understand, it doesn't matter if you start with 2, it doesn't matter if you start with -1, so pick one and go there, okay? So I'm going to do synthetic. This should be nothing new to you. Okay, and I get a 0 remainder, which is good. So I know -1 is the solution, but I also know, because I graphed it, that -1 can be used twice. So I started out with the fifth degree function, and now I'm down to a fourth degree function, and I'm going to do synthetic off of where I left off. And I'm going to use -1 one more time because I know it should be a repeated solution. So let's do it again. Okay, and in doing that process again, I get a 0 remainder, which is no big surprise. So I know -1 is a repeated solution. Now, I've used it twice, and I told you if you have a repeated solution, it's not going to work more than twice. So I am done with -1, and I'm down to a cubic, right? Because I did synthetic starting with fifth degree, did it once to get down to fourth degree, did it again, and now I'm down to third degree. So what am I going to do? I'm going to keep going. So, like I said, this problem gets really big. I know that my other solution is at 2, so I'm going to do it again using 2. Okay, and doing the synthetic process again using 2, I see that I get a 0 remainder. So I know 3 solutions, and I am down to a quadratic function, and I'm going to solve that quadratic to get my remaining 2, which I know are imaginary because I can see that from my graph, my remaining 2 imaginary solutions. So take a second, you try this. This should be nothing new to you. Use the quadratic formula to solve for the remaining 2. Okay, so using x equals the opposite of b, that'd be a positive 4, plus or minus b squared, negative 4 squared is 16, minus 4 times 1 times 7, so that'd be 28, all divided by 2a. And then if we simplify, 16 minus 28 is a negative 12, all divided by 2. And I know that 12 is, well, negative 12, first of all, that's going to be imaginary, but I also know that 12 is 4 times 3, so that's going to be 2i root 3. And then this 2 divides into both of those. Don't forget that it's dividing into both of those. So last but not least, I'm going to have to squeeze this in. I get 2 plus or minus 1i squared of 3. So there are my 2 imaginary solutions, and I know it crossed at a positive 2, and I know that negative 1 was a repeated solution, and you don't have to write that twice. So here it looks like I have 1, 2, 3, 4 solutions, but I know that this is a repeated solution. You can certainly reference that, but it's not required. As long as you find all the solutions, you're done. So again, quite a hefty process. Let me just remind you, I won't overlap those, that you graphed the 5th degree function, you saw that it touched the x-axis, so that counts as 2 solutions. It crossed the x-axis, counted as a third. Take all 3 of those, work your way down to your quadratic, and solve that quadratic to get those remaining 2 imaginary solutions. Alright, I'm going to walk through one more example, but I want you to pause the video and I want you to try this on your own. Okay, so pretend this were an exam. Yes, you could use your calculator. However, you still have to show me all the work. So find all the zeros. All right, let's see how you did. So off to the side, I've just sketched a graph of what this 4th degree function looked like on my calculator, and it crosses at negative 1 and 4, crosses all the way through. So I know they don't count as repeated solutions. So I have 2 real solutions, which means the other 2 are imaginary. So here I go, working my way down from 4th degree to quadratic, so I can find the remaining 2 solutions. So I'm starting with negative 1. It does not matter if you start with negative 1 or 4. And I'm going to do the synthetic process, of course. And I already made a mistake here, sorry. Let me cross this out. 13 plus 8 is 21. Negative 21, so negative 20, and positive 20, so yes, I get a 0 remainder. Okay, so I started with 4th degree, did synthetic to get down to a 3rd degree, and I'm going to bank off that and use my other real solution of 4 and see what I get. Okay, and I got, of course, a 0 remainder again, which brings me down to my quadratic. So now I'm going to solve that quadratic by completing the square using the quadratic formula, and I usually use the quadratic formula. So x equals, okay, so I've got the opposite of b, plus or minus b squared, minus 4 times a times c, all over 2a. 16 minus 20 is negative 4, and the square root of 4 is 2, but it's also imaginary. So I'm going to have 4 plus or minus 2i, all divided by 2, and I'm going to divide both pieces by 2. So I get 2 plus or minus 1i, and there are my 2 imaginary solutions. And then it crossed at negative 1 and positive 4. So there are my 4 solutions. 2 are imaginary, 2 are real.